Okay, we are going to solve conceptual question for work and energy. Let's go to read the first question. It says, two men, Joel and Jerry, push against a car that has stalled trying unsuccessfully to get it moving. Jerry stopped after 10 minutes, so he's pushing, but the car doesn't advance, while Joel is able to push for 5 minutes longer. Compare the work that they do on the car. So this is the idea. Work is force by displacement, is the force in the direction of the displacement. So you push in some direction, so the work is the force, the force in the direction of the displacement, multiplied by the magnitude of the displacement. The work can be positive or can be negative. If the force is in the opposite direction of the displacement, the force in the direction of the displacement is this one, and the work will be negative because the force will go in this direction and the displacement will go in this direction. So the work is negative. But in this case, the work is not positive, not negative. The work is zero because the displacement is zero. So no displacement means no work. Let's go to the next question. This question say like this. You have a bucket. The bucket has a weight. I suppose it's a 35 newtons bucket. The weight of the bucket is 35 newtons. Is lifted vertically 3 meters. And then he returned from his position to his original position, this position. The question says, how much work did gravity do on the bucket? This is the force of gravity. We are going to calculate the work done by the force of gravity going up. And later on, we are going to calculate the work done by the force of gravity going downwards and returning to its original position. So first step, going up, the force, the weight, is in the opposite direction of the displacement. So the work is negative. And what is the work done by the weight, by this force? By this force is the force in the direction of the displacement multiplied by the displacement. The displacement is delta y, going up, positive. And the force in the direction of the displacement is minus mg. So the work going up is negative. The other way to see it is like this. The work is the magnitude of the force multiplied by the magnitude of the displacement by the cosine of the angle that makes the force with the displacement. The force is going in this direction. The displacement is going in this direction. The angle that they form is 180. Cosine of 180 minus 1. So the work is minus mg by the magnitude of the displacement. Okay, so going up, the work going up due to the weight is this amount. Going downwards, the force is still the same force, mg. I'm going from this position to his original position. Now the weight, the force, is in the direction of the displacement. So the work is the force in the direction of the displacement multiplied by the displacement, and this work is positive. If you want to do it in the other way, the work is the force by the displacement, the magnitude of the force by the magnitude of the displacement, two positive quantity by the cosine of the angle that they form. But the angle that the force and the displacement they made is 0 degree, and cosine of 0 is 1. So the work is the magnitude of the force by the magnitude of the displacement by 1. And this is, of course, positive because the magnitude of the force is positive and the magnitude of the displacement is positive. So the work is positive and have this amount, mg delta by the magnitude of delta y. This is going downwards. So the total work is the work going up plus the work going downwards to his original position. So it's the work going from position A to position A, or the work done from position A to position B, and later on from position B to position A. Okay, so the work going up is this amount, negative, and the work going up is the same amount but positive. The total work, 0. So the work that the weight is doing going up and again going downwards is 0. Kinetic energy. Which one has larger kinetic energy? A 500 kilogram object moving at 40 meters per second or 1,000 kilogram moving at 20 meters per second? Well, you will say like this to solve this problem. The kinetic energy is 1/2 of the mass by v squared. So you may say, okay, I will plug in the numbers. The mass is 500 kilograms. The velocity is 40 meters per second, so it's 40 squared. And in the first case, this is the total amount of kinetic energy. In the second case, the mass is 1,000 kilograms. You double the mass, and the speed is half. So you will compare, so the kinetic energy of the second object is 1/2 the mass by 20 squared. Who has more kinetic energy, this one or this one? Well, you have to calculate, you have to make numbers, you have to use your calculator. But the way to do it is not to use your calculator. The way to do it is like this. In the first case, I have the mass m0, the 5 kilogram. And I have kinetic energy, 1/2 m0 v0 squared. This is the kinetic, the mass of the 500, and this is the velocity 40 meters per second of the first object. Now let's go to find the kinetic energy of the second object, of the second object that have mass, double mass. The kinetic energy of the second object is 1/2 the mass of the second object by the velocity squared of the second object. But the mass is the double of the previous mass of m0. And the new velocity is half. So if you make a simple calculation, 2m0 will appear here, and here will appear v0 squared divided by 4. If you reorder this in a clever way, you will leave the 1/2 here, 1/2 here. 2 divided by 4 is 1/2, so it will be 1/2 m0 v0 squared. So, but what is this? This is the kinetic energy of the first object, or 1/2 of AK0. So the result is that AK, the second object, have, even they have more mass and less velocity, have 1/2 of the first object. So what is the correct answer here? Is the second object is the 1,000, so the 1,000 have the half of the 1,000. Who will have which one has larger? Well, the 500 has larger. The 500 object is larger the amount of kinetic energy, because the amount of the kinetic energy of the second is 1/2 of the first. And this is the way to solve. Of course, if you make numbers here, you will find that this number is bigger than this number. Okay, let's go to the next question. Kinetic energy. A truck has 4 times its mass. So the mass of the truck is 4 times the mass of a car. And it's moving with twice the speed of the car. The velocity of the truck, the magnitude of the velocity of the truck is 2 times the magnitude of the velocity of the cart. If Kf and Kc refer to the kinetic energy of the truck, compare one with the other. This is what we have to do. So it's the same logic that we apply on the previous problem. The K of the truck, the kinetic energy of the truck, is 1/2 the mass of the truck by the velocity of the truck squared. Now we substitute the mass of the truck. This is the kinetic energy of the truck. Now the mass of the truck is 4 times the mass of the car, mc. The velocity of the truck is 2 times vc. 2 times vc. So we make a simple calculation and will be 2 squared is 4. 4 by 4 is 16. So it's 1/2 16 mc vc squared. So we'll interchange the 1/2 with the 16 and will be 16 times 1/2 mc vc squared. But mc 1/2 mc vc squared is the kinetic energy of the object, the car. So the result is that K of the truck is 16 times K of the car. The kinetic energy of the truck is much more bigger than the kinetic energy of the car in this case. Let's go to the next question. Okay, let's go to solve this question. It's about the theorem of work and energy. The theorem of work and energy says that when you have an object, there is only, in this case, there is only one force acting on the object. The work done by the total force, in this case, only one force, that is the friction force. If there are more forces, I have to calculate the work of each force. The total work done, this is equal to the variation of the kinetic energy, or K final minus K initial, or 1/2 mv final squared minus 1/2 mv initial squared. So the total work, what produce work, what produce F by delta X, it produces a change in the kinetic energy. This change can be positive or can be negative depending if this is negative. In this case, the force by the displacement is negative, so the change in the kinetic energy is negative. So they say that they have two cars, the car L and the car N. The car L is the massive one, or the most massive car is the L, okay. And the less massive car is the N. So this is the light one, the N. So the work is the work done by the friction, is the only force that is acting on the body. They start, let me see, with the same speed. So they have an amount of kinetic energy, initial, 1/2 m by the same v squared. But in this case, the massive one have more amount of initial kinetic energy because his mass is bigger. So this is the amount of the kinetic energy. So the work is the change in the kinetic energy. They will stop. So the change in the kinetic energy will be this one, because K initial plus the change in the kinetic energy is K final. And K final is 0. So this is the change in the kinetic energy. It's negative. So big change in kinetic energy. For the second object, the kinetic energy is smaller because it has a small mass, the same velocity, but a small mass. So this is the amount of kinetic energy smaller than before. So he has to go to final kinetic energy 0. The change is here. This is the change. This is the change in the kinetic energy. So a small change in kinetic energy. But the work is the change in the kinetic energy. So here I have a change in the kinetic energy that is negative, and is big. Is big, is more negative, this work, than this work. So let's say that this is minus 100 joules, and let's say that this is minus 10 joules. Now the question say, for which car is the amount of work? Well, the amount of work, if you take it in absolute terms, here is bigger, but indeed minus 100 is smaller than minus 10. You have to be careful with this. So the other way to see it is like this. Okay, the total work done by the total forces is the change in the kinetic energy. Final 0 minus initial. So this is big and negative because the mass is big. For the object n that it have the same velocity, the change in the kinetic energy is final 0, initial minus 1/2 mv squared. So he goes from this initial kinetic energy to 0. So a small change in the kinetic energy. So the absolute value of the work of that is done on the massive object, the L, is bigger than the work that is done by the friction force on the object N. The other way to see this problem is like this. The work done by the friction force is negative the force by the displacement. The force is mu by n, by the displacement. So the work will be minus mu by n, the friction force by the displacement. Now the normal is mg. In the case of the massive object, will be capital M by g by the displacement. The work of the normal force is the same thing, is the force in the direction of the displacement multiplied by the displacement. So it's minus the force in the direction of the displacement, that is the friction, minus mu by the normal. But the normal now is not capital M, it's little m by g, because it's the work on the object n that is the less massive, little m, multiplied by the displacement. You don't, using work and energy, you may think maybe delta S is different than delta S prime. Maybe. So if delta S is different than delta S prime, I cannot compare this. I know that capital M is bigger than little m, but how I will compare if I don't know? But if you apply Newton's law, you will see that the two objects initially they have the same velocity, and the friction force in this case is smaller. The friction force is smaller here than here. Here is bigger. Why the friction force is bigger? Because the friction force is mu by the normal. So because m is bigger, the friction force is bigger. But you need to, maybe you think, okay, if the friction force is bigger, so he will stop before than this one. But it's not true. Why? Because Newton's law say that the total for the friction force minus mu mg equal the mass by the acceleration. So the acceleration is minus mu by g. Oh, it's a acceleration that is negative, is in the opposite direction as the velocity. So this is the acceleration in the first case. In the second case, you would say the total force acting on the body, the only one, the friction force, it will be minus mu by mg. But the total force is the mass by the acceleration. or the mass will cancel, and I have the same acceleration negative. So the same acceleration will produce the same displacement delta s. So delta s is equal to delta s prime. And now I can compare the work, and I can say that because this mass is bigger, this work is more negative than this one. So the amount of work, the work of L, in amount, in magnitude, is bigger than the amount of work on the object N. And this solves the problem. Now let's go to solve problem 6. It says like this: work and energy. You press the brake on your car in a panic and skid at certain distance. If you had been traveling twice as fast. So, would the car have a sky under the same? What distance would have a sky? Okay. So you start here and you are with velocity v. You press the brakes. When you press the brakes, you eventually you will arrive to velocity 0, and you have performed a displacement delta x. Who has made you to change the kinetic energy? The friction force. The friction force, the work done by the friction force, is equal to the change in the kinetic energy. So the change in the kinetic energy is final minus initial. So this is negative because final is 0. Initially is some positive amount. So this is negative. So the work is negative. Also the force is going in this direction, the friction force, so will produce a negative work. So this is negative, and of course if this is equal to this, this is also negative. So let's go to analyze how you will find the displacement that occur. So let's say the first case, the object is moving with velocity v. So he displaces a delta x. How you will calculate this delta x? You will say the work is the change in the kinetic energy. What is the work? The work is the force by the displacement. In this case, the force is the friction force. So this work will be negative because the friction force is in the opposite direction as the displacement. Okay, the work will be minus the magnitude of the friction force by the magnitude of the displacement. So this is the work. So what is the displacement? The magnitude of the displacement in this case, when the object is moving with velocity v0, it will be delta x0. If you solve for delta x0, let's go to put here delta x0. If you replace the data, v final is 0, so it will be minus 1/2 mv0 squared, the initial velocity. So minus 1/2 mv0 divided by the minus the friction force, this will be the displacement. And this displacement, of course, is positive, because this minus with this minus will be positive. The magnitude of the friction force is positive, so everything will be positive. So the amount of displacement that occur in this case is 1/2 mv0 squared divided by the friction force. Now in the second case, where you are moving with double velocity, the friction force is the same one, is mu by the normal. Nothing have changed. Mu have not changed, mg have not changed, so you have to suppose that you have the same friction force. So the new displacement when the velocity v0 is double will be minus 1/2 m by the new velocity 2v0 divided by the same friction. minus minus plus 1/2 m 4 times v0 squared divided by the friction force, by the magnitude of the friction force. If you compare the two results, you will find that the new displacement is 4 times, you take this 4 here, this 4 out, and this amount is exactly the old displacement when the object was having velocity v0. So the new displacement is 4 times the old displacement. So if you are going to double velocity, you will displace 4 times the old displacement that the object was performing when his velocity was only v. So that's why there is limits in the velocity when you use your car. And this is why it's important to keep distance. Because if you are going to double the velocity, in order to stop, you need 4 times the distance to stop. Okay, let's go to the next problem. Next problem. Okay, let's go to read this problem. It's you and your friends who weights the same as you, so they have the same mass, both of them, want to go up to the top of the tower. Your friend takes the elevator, so he takes the elevator. He goes up from the floor to the top of the tower. So he displays a distance delta y in this direction. And the force is going in this direction. So the work is the force in the direction of the displacement minus mg by the magnitude of the displacement. So the work is minus mg by h, being h positive, this h. So this is the work, it's a negative work. So what is asking the problem is compare the work with the work that you have done if you go, let's say, through the stair in this direction. Now, if you go to the stair in this direction, the work will be the force in the direction of the displacement. This is this force. This is this force, the mg sine of theta. By the displacement, this is the displacement, the magnitude of the displacement. Remember, is the force in the direction of the displacement, positive or negative, multiplied by the displacement, the magnitude of the displacement. So this work, it will be negative. But what happened? That sine of theta is opposite divided by hypotenuse. So sine of theta is h divided by delta s, by the magnitude of delta s. So the work will be minus mg by sine of theta h by the magnitude of delta s. Delta s will cancel, and the work will be minus mgh, which is the same work that has been done when the guy takes the elevator. Of course, the elevator, the work of the is asking about the work done by the weight of the person. Okay, in both cases, the work of the weight mg is the same one. It doesn't depend on the path that you take. Whatever any path that you take, the work will be the same. And this is the meaning of a conservative force. The weight is a conservative force because the work done from going to a point to another point is the same wherever the path that you choose. Okay, let's go to question 8, springs. It says the graph show the magnitude of the force. So a positive quantity of the force exerted by a spring as a function of the distance x. The spring has been stretched. For which one of the graph does the spring obey Hooke's law? So which of the graphs represent Hooke's law? So Hooke's law says that the force is minus k by the displacement. If delta x is positive, the force is negative because k is positive always. So if delta k is negative, the force will be positive. So the representation of the force is, if this is the 0 and delta x is positive, the force is negative. So on here, the force is negative, means that it's going to the left. So you stretch and the force is going to the left if you displace to the right. And at the same time, if you displace to the left, the force is positive, means that it's going to the right, the force. So, because he's talking about the magnitude of the force, indeed the graph that we have to see is this one. This one, the magnitude of the force, the magnitude of the force as a function of the displacement. So this one, no, because the force is constant, never change. So this is a constant force. This is a force that increases with the distance, but it doesn't increase linearly. It increases like a parabola. It looks like a parabola. So it has more slope. This happens the same thing. It doesn't conserve the sign because cannot be, because it's talking about the magnitude of the force. This force is negative. I have to maybe to draw something like this have more sense, but the force has to be linear, not so. The only option is this one. Okay, so let's go to the next problem. It's a energy conservation. This is a with conservative force. Conservative force are the forces where the work doesn't depend on the path that you choose. When this is happened, the mechanical energy at any point is equal to the mechanical energy at any other point. So it's a swimmer at the water, although both slide. So this swimmer is slide on a surface that is on a path that is like this one, while this swimmer is slippery on this path. So it's say, although how does the speed v1 on a swimmer reaching at the bottom, slide 1, compare the magnitude of the velocity? Because the direction of the velocity here is going in this direction. And the direction of the velocity, it will be in this direction. They don't have the same vector velocity, but the magnitude will be the same one. Why? Because you apply conservation of mechanical energy. And the conservation of mechanical energy would say that at the point A, there is kinetic energy plus potential energy. The kinetic energy, it is assumed to be 0. The potential energy will be mgh. So it will be kinetic energy 0 plus mgha equal kinetic energy at the point V, 1/2 mvv squared, plus potential energy 0. mgh is 0 at the point V. So the velocity of the object V will be V sub V squared equal GHA. But the same equation will happen if you place it here between these 2 points. You will obtain the same result that if you place the equation between these 2 points. The only force that is doing work here is the weight, mg. Because the work done by the weight is the same and going from A to B because it's a conservative force, we can say that at the end, the magnitude of the velocity will be the same, but not the direction. Okay, let's go next problem. Power. A force produces power P doing work W in a time t. So the power is the work produced, work done, in the time that he is doing the work. So in the elapsed time, you can do this work. So the power produced by a force that does 6 times as much work in half of much time. So the work will be the force by the displacement. The force in the direction of the displacement, Fx, can be positive, can be negative, by the amount of the displacement. The amount of the displacement is delta x. Divided by delta t, so the work, the power is force by velocity, because delta x divided by delta t is velocity. Now, the new power P prime, how will be compared with P0? Well, the new power P prime will be the work done in the time that you takes. The work done, he said, that is 6 times the all work. And the times is half of the time. So what would be the new power? 6 divided by 1/2 is 12. So 12 times omega 0 divided by delta t0. But omega 0 divided by delta t0 is the power, the initial power in the first case. So in the second case, P prime is 12 times P0. Okay, let's go to the next question. It's a power. If the unit of your answer are kilograms meter square second cube, kilogram, which of the following types of quantities could be your answer? So kilograms per meter square divided by second cube is the same that kilogram meter second square meter second. This is force, this is velocity, this is power, so this is watts of power. So this is the correct answer. Let's go to the next one. It's a energy conservation with non-conservative force, so there is friction. Or a heavy sled and a light sled, both moving horizontal. To solve this question is about energy conservation with non-conservative force. When there is non-conservative force, there is no energy conservation, but doesn't matter. It's say like this: you have an object that is moving. Here, the key question here is to realize that they are moving with the same kinetic energy. You have one that is massive, capital M, and one that is light, little m. So if they have the same kinetic energy, is 1/2 m1 v1 squared is equal to 1/2 capital M v2 squared. If k1 is equal to k2, it means that the velocity of the light one is bigger than the velocity of the massive one. Okay, because it's clear that if you have a 1/2 mv1 squared for the light one, and you want to give it mv2 squared, so take the 1/2. So if you multiply a little m that is smaller by something, you need here bigger amount, because here is something big should be multiplied by something smaller. So V2 is smaller. So mv1 squared, so let's say that m, to see clear, let's say that m is bigger, is 10m. What is the relation with the velocity? It will say 1/2 mv1 squared, it will be 1/2. Now the m is 10 times m, 10 times m, v2 squared. So the 1/2 will cancel, the m will cancel. So what we'll say is that v1 squared is 10 times v2 squared in this case. So the v1, the less massive, will be with velocity always bigger than the other one. This is the first key question when they say they have the same kinetic energy. Now they have a friction force. Now the friction force, which one will be bigger? The friction force is mu by the normal and have the opposite direction as the displacement. Let's say that the displacement is going to the right. So the friction force are the same in both cases. Well, the normal in the first case is mu mg. So now the friction force will be bigger because the m will be bigger, because the friction for the second case will be mu also by the normal, but now the normal is mu little m by g. Wow, so here I have a bigger force than here. But here I have big velocity, small amount of friction. Here I have a small amount of velocity, big amount of friction. So what it says is what happened to the mass m. What happened to the mass m, that the friction makes work, and the work makes a change in the kinetic energy. This is our theorem of kinetic energy. So what is the work done by the friction on capital M? The work done by the friction on capital M is the force by the displacement. The force in the direction of the displacement, because the friction force is always in the opposite direction of the displacement. The work done by the friction is minus Fr by delta x. So it will be minus mu mg by delta x. And the work is the change in the kinetic energy. And the change in the kinetic energy is K final minus K initial. When he stops, K final is 0. So the work minus mu capital mg delta x of the mass capital M will be 0 minus Ki, K initial. So delta x will be, solving for delta x, the delta x will be minus Ki divided mu by mg. So you can see clearly that this is the expression for the displacement. For the delta x little m, it will have the same calculation. You can do it again. The friction force will be mu by the normal, but the normal now is little m by g, is a small friction force. The work done by the friction force is minus Fr by delta x of the little m. It will be minus mu mg, that is the friction force, by delta x of the little m, delta k, 0, ki. The same ki that appear here, because the problem say that it has the same ki. So the displacement that suffered the mass little m will be the same expression, minus ki divided by mu mg. What is bigger, delta, the displacement of the little m, or the displacement of the capital M? So if m is bigger, delta x is smaller. So it means that for the massive one, delta x is smaller. Or delta x, this one, is bigger than this one. Delta x of the capital M is smaller than this one, or what it's the same, this one is bigger than this one. So now we go to to read what it say here. It say, the heavy sled would slide further on the rough snow. No, this is not our conclusion. It's exactly the opposite one. That the light one, when the m is bigger, the delta x is smaller. No, he say further. No, the a is not here. Both sled will no, they will not slide the same distance. The massive one will slide less displacement than the light one. The friction from the snow will do the same amount of work on both legs. No, because they have different mass. So this amount of work here, the work of the friction, will be mu mg delta O, maybe. Yes, it will do the same amount of work because it's the change in the kinetic energy, and it's the same change in the kinetic energy. Wow, it's the same amount of work. This is true. The friction force, the friction from the snow will do the same amount of work on both. Sled is true. They will do the same amount of work. The work is the change in the kinetic energy. It has the same change in the kinetic energy. Yes, it will do. This is true also. This is true. Let's go to read the second one. Let me read it again. The friction from the snow will do the same amount of work. The work is the change in the kinetic energy. They start with the same kinetic energy and the end with the final kinetic energy 0. So the change in the kinetic energy will be the same. The friction force, the friction from the snow will do the same amount of work. Yes, this is true, I think. Yes, no doubt. On the route D, on the rough snow will change in kinetic energy will be the same for both of them. Wow. On the rough snow, the change in kinetic energy will be the same for both sleds. And the change in the kinetic energy is true also. They will be the same. Change in the kinetic energy will suffer from starting from the beginning and from the end. They start with the same kinetic energy, and they end with the final kinetic energy, both of them with 0, so they have the same change. So on the rough snow, the change in kinetic energy will be the same for both sleds. It looks that is true also. This is the conclusion that we get. The light sled will slide further on the rough snow than the heavy sled. This is the one that we found in our analysis doing the problem. But these two, C and D, it looks that they are correct also. Let me read it again. The friction from the snow will do the same amount of work on the friction. It will do the friction, the work done by the friction. The product will be the same because it's the same change in kinetic energy. C is true. And V, it say on the rough snow. What do you mean on the rough? Suddenly onto the snow and eventually comes the slave. The same for both. Which of the yes? On the rough snow, the change in kinetic energy will be the same for both sleds. Yes, on the rough snow, they will suffer the same change in kinetic energy. This D is also correct. But the one, I suppose that the one that he wants you to say is the E. The E is the interesting one. The light sled with a slide further than the rough snow, than the rough one. Okay, that is a heavy sled. Well, this is the problem. It's a good analysis what we did. It's not so easy. They have many details on this problem. You have to be careful with this kind of problems to analyze correctly. Let's go to the next problem. Okay, let's go to analyze the question 13. It say Energy conservation with conservative force. A heavy stone and a light stone are released from rest in such a way that they both have the same amount of gravitational potential energy, just as they are released. Okay, the potential energy U is U. So the potential energy of the mass of the little m is mass by acceleration by g by the h of m. And the potential energy of the capital M is mass by g by the h that the capital M has, that I'm calling h sub m. What the problem is saying here, that is a little bit tricky, is that the potential energy are the same. This doesn't mean that the h is the same. Saying that the potential energy of the mass m is the same that the potential energy of the capital M of the massive one is to say that mghm of little m equal mg of h sub m. So if you cancel the g, we would say mhm equal capital M of hm. So if you solve for hm, of h little m will be m divided by m by h sub m. So if m is greater than little m divided by m is greater than 1. So h sub m is greater than h sub little m is greater than h sub m. So the condition that they are giving us in this problem is here. Here, the h sub m, little m, is launched with a bigger h than capital M. So if it's launched with a bigger h, they have more potential energy. So because when it arrives to the floor, potential energy plus kinetic energy will be these amounts. Okay. But when it arrives to the floor, all the potential energy that is here will be converted into kinetic energy. Now the velocity at which it arrives will be bigger in this case because the h is bigger than in this case. So let's go to do the equation. So here is the point where it arrives h equals 0. Here is the point where it arrives h equals 0. I want to compare the velocity of little m with the velocity of capital M when both arrive to the floor. So this is the point A, and this is the point A prime. This is the point V, and this is the point V prime. When it arrives to the floor, mechanical energy of the mass little m at the point A equal mechanical energy of the mass little m at the point V. And the other equation that we are going to use is that the mechanical energy at the point A prime equal the mechanical energy at the point B prime, that is the same that V because it's arrived to the floor, and this is for M and this is for little m. For little m, the mechanical energy initially is m g h m, h of the capital M, that is bigger. And the mechanical energy is all kinetic energy, VV squared, VV of the capital M. So the M cancel, and the velocity of the capital M, of the little m, when it arrives to the floor, will be 2 times G by HM. Let's go to do the same thing with the capital M. The mechanical energy of the capital M at the point A prime is capital M G by the H of capital M. Kinetic energy, nothing at the point A prime. At the point V prime, that is the same point V, when it arrives to the floor, it will be kinetic energy 1/2 The mass will be capital M by the velocity v at the point V of the capital M square. Kinetic potential energy 0. So what it says this equation, I can cancel the Vm. So what it says that 2 times G h of the capital M equal Vv squared of the capital M. So the question is, what is bigger? This velocity when it arrive to the floor or this velocity? Well, this velocity is bigger. The light one will arrive to the floor with a bigger velocity because the h is bigger, 2g. The h is bigger, the h of the little m. So the velocity of the little m is bigger than the velocity of the capital M. Now let's go to read. Remember this and don't be confused. When you launch two bodies, little m and capital M, the acceleration, the gravitational acceleration, does not distinguish between the mass of the object. The acceleration is g for both cases. So if you launch two objects, of one with little m, the other one with capital M, from the same h, they will arrive with the same velocity as the floor because they have the same g, the same acceleration, the same change in velocity per unit of time. So the object will arrive, both of them, with the same velocity. But this is not the problem that we are discussing. The problem that we are discussing is that they have the same potential energy, amount of potential energy, mgh equal capital MGH. This is different question. So now let's go to read what the problem say. What the problem say here, it say the stone must have released from the same height. No, this is not true. This is not true. No. The initial height of the light stone is greater than the initial height of the heavy stone. Yes, this is true. The only way to make U sub m equal U sub m is that the h of little m, it will be bigger than the h of capital M. So this is true. The stone both have the same speed just as they arrive to the ground. No, this is not true. We found that what we found is that the velocity here of little m, the velocity of the little m here is bigger than the velocity of the capital M because the h is bigger. Okay. I think that I'm not making a mistake. Let me see. So just as it reached the ground, the light stone is traveling faster than the heavy stone. Yes, it's true. Yes, this is true. The light stone have more velocity, little m has more velocity because the h is bigger. Oh, you see, compare this one with this one. Compare this with this equation, and you would see that if the hm is smaller, will produce a bigger amount of v squared. Okay, so it's true. The E is true, and the E, it say the stone both have the same kinetic energy as they reach the ground. So to answer correctly this question, we see that the little m is launched with a bigger height, but the potential energy, it say the problem that have the same potential energy here, the objects, the little m have the same potential energy that the capital M. So when it arrived to the floor, the little m, have no potential energy, and all the potential energy is converted into kinetic energy. So if we apply the conservation of energy by little m, we'll say that at the point A, U sub m at the point A plus kinetic energy at the point A equal kinetic energy at the point V plus 0. So the kinetic energy at the point V of little m will be U sub m. If I do the same thing for the mass capital M, I will say the U of the capital M, that by the way is the same potential energy of little m, plus the kinetic energy is 0. This is equal to the kinetic energy at the point V of the mass M plus potential energy is 0. So the kinetic energy of the point V at the point V of capital M and the kinetic energy at the point B when the potential energy is 0, in the first case the kinetic energy is U sub little m. In the second case, the kinetic energy is U capital M. But this U, this potential energy and this potential energy is the same one. So the kinetic energy when they arrive to the floor is the same. Is the same kinetic energy. So when they arrive to the floor, all the kinetic energy, all the potential energy that is have here, no kinetic energy, is converted into kinetic energy and potential energy is 0. It happened for both of them. So this is true also. Wow. Wow, it's a tricky questions. Okay, think about it and let me know if you have any doubt. Let's go to the next question. So let me read it to see what happened. Energy with conservation. A stone can slide down on 4 different frictionless ramp. So for which ramp with the speed of the ball will be greatest at the bottom. The speed means the magnitude of the velocity. Now when he goes through here, the vector velocity, it will go in this direction. When it goes to here, the vector velocity will go in this direction. When it goes in this path, the vector velocity will go also in this direction. What is asking the problem is the magnitude of this velocity, the length of the vector, the magnitude, not the direction, the magnitude of the vector will be bigger in this case, or in this case, or in this case. So you will do like this. This is the point A, and this is the point V. The mechanical energy at the point A is mgHA, equal the kinetic energy at the point A. You always, the stone is the same one with the same mass. So the kinetic energy is 1/2 mvv squared plus potential energy at 0. So 0 kinetic energy plus potential energy equal kinetic energy at the V plus potential energy at the V. So the velocity vv squared, you cancel the m, it will be 2 times g by the h, HA. This analysis apply also here. A is the same h, so the velocity is always the same. So the speed of the ball will be the same in all ramps. Okay. Well, that's all. Let me see, there is a new question here. Let me see this question. It says energy conservation with conservative. When you drop a pebble from height h, it reached the ground with a speed v. It reached the ground with a speed v. So this is the ground, I suppose, and this is the velocity v when it arrived at the point v. If there is no resistance, from what height you should drop it so it will reach the ground with twice velocity. Okay, so you reach it from some unknown h. If you drop it from this h, mgh, the potential energy, plus the kinetic energy at the point A will be the kinetic energy at the point V plus the potential energy at the point V, which is 0. So always the velocity v sub v would be square root of 2 times g by the hh. Now the problem say for which h prime, for which h prime you need to launch to have double velocity. So you will say the potential energy at the point h prime, the unknown h prime. So this is h, and you suppose that there is an h prime where you are launching here. So here it arrives with velocity v, and you want the object to arrive with double velocity, 2 times v. So what is the h prime? How it's compared the h prime with the h to make possible that the object will arrive with double velocity when he hits the floor. Well, this is the floor. Okay. So you will say the mechanical energy at this point, mgh prime, will be equal to the potential energy at the point V, 0, plus the kinetic energy at the point V, 1/2 m by the velocity square. But I want the velocity to be the double. So I want to know how to relate the h prime with the h that is here. So gh prime will be 1/2, 2 squared is 4, 4 times v sub v squared. 4 divided by 2 is 2, 2 v sub v squared. But the velocity at the point V of the first one is 2gh. So I have related the h with the h. The g will cancel here, so h prime will be 4 times h. The g will cancel, so you need to launch the body, h prime, 4 times h in order to achieve the condition that when it arrives to the floor, it will arrive to double velocity. So to arrive an object to double velocity, you need to make the h 4 times. 4 times the h is the h prime. It makes logical. Let me think if I did it correctly. So let me check it. Here is the checking. Now, let's go to see. Now I apply again conservation of mechanical energy for the body that is at the h prime. And the h prime is 4 times h. The potential energy will be mg by his h, 4h, or h prime. So kinetic energy is 0. So this mechanical energy at the point A is equal to the mechanical energy at the floor. At the floor, the potential energy is 0, and the mechanical energy is 1/2 mv prime v sub v squared. So, what is happening? These two will go here, and we'll say 8 times 4 by 2 is 8. 8 times g by h will be v prime v sub v squared. So v sub v prime squared is 8 times 4 by 2 gh, 4 by 2 gh, so v prime v sub v squared is 4 times, 2 times gh, or let's go to put the h correctly, the h, 2 times gh is v sub v squared. So the velocity prime when you launch the body for 4 times the h, the velocity is the double, because v sub v is the square root of 4 times v sub v squared, and this is v sub v prime. So v sub v prime, when it arrives to the floor, is 2 times v sub v square root of 4 by square root of v sub v squared. So it's 2 by v sub v. Oh, so I did it correctly. Okay, I've checked it. So if you have an object that it is still, I'm trying to think if it's reasonable, this. I think it's reasonable, but let's go to see it. So I think it's reasonable. You launch the body for the HH, and the body arrives the floor with velocity v. Now you launch the body for 4 times h. H prime is 4 times h, and it will arrive with double velocity. So they are not proportional. So the correct answer is for h. And just to be sure, let me read it again. The problem: when you drop a powder from h, it reaches the ground with velocity v. From that, what h should be dropped so it will reach the ground with twice velocity? Yes, if you drop it with 4h, it will arrive with double velocity. So this is the result. And this is the power of applying mechanical energy, conservation of mechanical energy between 2 points. This is the correct answer. I think that I didn't make any mistake. If I made a mistake, please let me know.